All right, guys, in this video, we're going to be going over the Ksp review and Qsp practice. So basically, this is going to be a practice problem that basically covers all the concepts from 4-4. So just equilibrium, but more specifically, the equilibrium of salts dissolving in water. So specifically, Ksp problems. Okay, so these types of problems, the things you should be thinking about are, figuring out the concentrations of the different ions when a solution is saturated. And remember, saturation means you're at equilibrium. And then also kind of understanding the idea of when will you see a precipitate. So like, for example, if I mix barium nitrate and sodium sulfate, I should be thinking that barium sulfate's going to precipitate. But now, right, we can't just go on solubility rules. Insoluble compounds will always precipitate, and soluble compounds won't precipitate. Soluble compounds can precipitate if you get the concentrations high enough. So basically, if your solution is oversaturated with those ions of a salt, then some of those ions will stick together and then precipitate out of solution to bring the concentrations back down to the saturation point. So now, if you're asked what will precipitate, if you're asked for a net ionic equation, that kind of thing, for the most part, if you know barium and sulfate are going to be in solution, you can think that it's going to precipitate. If lead ions and chloride ions are in solution, they're probably going to precipitate. But if you're asked, will it precipitate? That's when you have to look at Qsp and compare it to Ksp. So let's go over that in these practice problems here. Okay. And then we were also talking about molar solubility. What is it? It's just the molar concentration, moles per liter of that salt in a saturated solution. And we should understand if we know the Ksp, or we know the concentration of one of the ions when it's saturated, or we know the molar solubility, then we can really calculate all of those values. And we just have to understand basically the stoichiometric ratios between the ions and the entire compound. Like, for instance, in lead fluoride here, if I know the concentration of lead, I would double that to get the concentration of fluoride. If I knew the concentration of fluoride, I would cut it in half to get the concentration of lead in a saturated solution, right? If I knew the molar solubility, that would be the molarity of the entire compound. That would be the concentration of lead, but you would have to know to double it to get the concentration of fluoride. The other thing to remember is our Ksp shortcuts, where Ksp equals x squared, Ksp equals 4x cubed, Ksp equals 27x to the fourth, all those things. The unknown, so Ksp is the solubility product, it's the equilibrium constant for the process, and then x, the unknown, sometimes it's referred to as S, like in College Board, that is the molarity of the entire compound. So if you can solve for that unknown, that is the molar solubility. Okay. All right, so let's just jump into it. So we have to write a chemical equation, including the states of matter, which shows the dissolving of this salt in water. So this is where, you have to remember lead, or like fluorine is diatomic, but not fluoride. So this is saying one lead ion and two fluoride ions. We have to know that each fluoride ion is 1 minus, and that would make the lead 2 plus also in the name lead 2 fluoride. It's telling us it's lead 2 plus. So it asks us to include the states of matter, so we need to do that. So we would write the lead fluoride on this side solid yields the aqueous ions. Remember, you don't include a water molecule. If you want to show, if you're doing a Ka or a Kb, where you have to show an acid acting like an acid in water or a base acting like a base in water, you have to include the water molecule. But if you're doing solubility product, it's just solid salt on this side yields aqueous ions, okay? But it's important to note that you get 2 fluorides. So if we were given the Ksp value, if we were asked to write the expression, we would say Ksp equals the concentration of lead times the concentration of fluoride squared, Okay, so it's important to know that that's there in case we have to write the expression, or if we're going to do some calculations with that expression, which we're probably going to have to do because we have the value of Ksp, and we're probably going to be looking for molarities or something. All right. So part B says calculate the solubility in moles per liter, so that's molarity. So it's asking for the molar solubility at 25 degrees Celsius. So we're going to just skip right to our shortcut. Let me move my head over on this side, and let me scroll down over here. Okay, so right, this is our salt. We got a 1-to-2 ratio, so this is our shortcut. Remember, this shortcut is basically making a rice chart with these. The lead would start at 0, the fluoride would start out at 0, but it would be plus X for the lead, and I should say plus S for the lead, and plus 2S for the fluoride. And then if we plug it into the expression, it would be S times 2S squared. Okay, so 2 squared is 4, and then S times S squared is S cubed, so this is the simplification. So remember, this is our shortcut. This is the solubility product. They gave us this number. We know what this number is. So all we're doing in part B is solving for S here. I always call it X. College Board calls it S to remind you that it's the molar solubility. So regardless, if you solve for that, that's going to be the moles per liter of the entire compound. Okay. So we do that. We solve for S. So what you would do is take this number, divide by 4, and then take the cubed root. Okay. So you have a calculator. You can work that out. It comes out to be, and a lot of times KSPs. A lot of times equilibrium constants only have 2 sig digs, so a lot of times when you're doing math involving any equilibrium constant for the most part, it's probably two significant digits you have to round to. So it comes out to be, if we round correctly, 7.7 times 10 to the negative 3, and again, this would have to have units, moles per liter, okay? So that's the molarity of the entire compound when it's saturated in solution at, I think the temperature on the worksheet says 25 degrees Celsius. Okay, now they didn't ask this, but let's understand what this would also mean, right? This is the molar solubility of the entire compound, the molarity of the entire compound. So since 1 unit of lead fluoride has 1 lead ion, that would also be the concentration of lead ions when it's saturated, but the fluoride would be double, right? Because you have 2 fluoride ions for every 1 lead ion. So this times 2 would give us the molarity of fluoride, just in case they asked that question. Okay. All right, so let's go back up. What's our next question? C. So it says, if a student needed to use 8 grams of the salt in the lab setting, how many milliliters of this solution, of the saturated solution, would they need to measure at 25 degrees Celsius? So understand, the molar solubility we just solved for is the molarity of a saturated solution. So that's moles per liter. We can use that to convert moles to liters or liters to moles. And so in this calculation, it's just dimensional analysis. We got to convert moles to liters, and they asked for milliliters, so then liters to milliliters. So it's 8 grams of lead fluoride divided by its molar mass, divided by the answer we got on part B, the molar solubility, and then times 1,000 to make it milliliters. All right, so let's see what that setup would look like. We take our 8 grams of the salt. They didn't give us the molar mass of lead fluoride, so we'd have to calculate it. So lead is 207.2, and each fluorine is 19, right? You get that on the periodic table. You add it up. A lot of times that'll be given to you. So 8 divided by that gives us moles, and then moles divided by molarity gives us liters, and then times 1,000. So when I do the math, I get 4,237 point something, something, something. But I'm really only allowed 2 sig digs because of the molarity, the molar solubility. So around 4,200 milliliters would be required. So to get 8 grams or around 8 grams, the student would have to measure, 4.2 liters of a saturated solution of lead fluoride to have that many grams of salt dissolved in it. Okay. All right. So back up to part D. All right, so this one's kind of weird. It says, what is the lowest concentration of fluoride that would be needed to begin the precipitation of lead fluoride? Okay, so understand, we have this, the Ksp that we have describes the equilibrium of this reaction, right? So we want to know, so imagine what we have in the container. We have lead ions in the container, and we're slowly adding fluoride, and we want to know, well, how much fluoride do we need to add to trigger the reaction to shift to the left, right? Because shifting to the left for a Ksp reaction would mean those ions are precipitating out of solution, right, forming the solid. Okay, so we know that this concentration is, the lead concentration is 0.001. And so the question is, well, what does this concentration have to be to make your solution saturated or, slightly oversaturated so that you'll trigger precipitation, right? That's basically it. So basically, it's just plug the numbers into the Ksp expression and you're solving for the concentration of fluoride, right? Because precipitation can't happen until you're saturated, right? And then once you're saturated, one more ion past that, boom, that'll cause the precipitate, okay? So we have the value of Ksp. They didn't say anything. Usually they would remind us that we're still at 25 degrees Celsius so we can use that same Ksp value that they gave us, but let's just make that assumption. And so now we just need to figure out what fluoride would be. But this is where we have to remember to square the fluoride concentration in the expression. Okay, so let's go look at that. Okay, so again, we need to determine the fluoride concentration, which will make the solution saturated in terms of this salt. So we have the Ksp, it equals the concentration of lead times the concentration of fluoride squared. And so when this side equals that side, that means you're saturated, and that means you'll get a precipitate, right? So, so we plug in the molarity of lead that's already in solution, and we solve for X. But again, don't forget you had to square the fluoride concentration. So you're solving for X, which is the fluoride concentration. So when you solve for X, that'll be your answer, right? So we solve for X, and so once the fluoride concentration hits 0.042 moles per liter in a solution that already has 0.001 moles per liter of lead, that's when lead fluoride would start to precipitate. Okay, so the answer is 0.042. This is kind of like a couple of the multiple choice questions you have in your concept check. So I just wanted to show you an example of those so you understand what to do there. Okay. Let's go back. Is that it for number one? No. Okay. So part E, we have a common ion question. So we want to know. Okay. So like understand what we did in part C. We figured out how many milliliters of solution 8 grams of the salt would be in if you just were dissolving the salt in pure water. But here we want to know, well, how many milliliters of water, and it just says volume, so we could stop at liters. So what volume do we need to dissolve 8 grams of the lead fluoride, but in a solution that already has fluoride in it, right? So in a 0.1 molar solution of sodium fluoride. So we have to recognize that fluoride's a common ion. So again, if you make a rice chart for a Ksp reaction and you get your equilibrium concentrations in terms of S or X, once you solve for that, X is the molar solubility. So what we need to do is figure out the molar solubility in this solution, not in pure water. Okay, so our answer to part B was the molar solubility in pure water. Now we need to know what the molar solubility is going to be in a solution that already has 0.1 molar fluoride. Okay, so that's what we're trying to get to. Okay, and then once we have that number, once we have that molarity, it's going to be the same exact calculation we did here, just with using a different molar solubility. So we would do 8 grams of our salt divided by the molar mass, divided by the molar solubility, times 1,000 if we wanted milliliters. But that's the deal. So this is a lot going on in this question. So it's common ion. We know that the salt's going to be less soluble, so the molar solubility that we calculate for to use in part E should be less than the 7.7 times 10 to the whatever. Okay, so this is the molar solubility in pure water. We know that the molar solubility in the presence of a common ion is going to be less than this. Okay, we got to calculate that, and then we got to use that in our dimensional analysis to figure out the volume of the salt. Okay, so let's go ahead and do that. Okay, where am I? I'm here. Okay, so again, a lot of you will be able to do this in your head, but remember, you can't use the shortcut if it's a common ion. So like the shortcut is only for if there's no common ion, or you're in pure water, you can use the shortcut where the unknown X is the molar solubility. But so all we have to do is make a Rice chart. So the lead is starting at 0, but the fluoride is starting at 0.1. The reaction has to shift this way a little bit to get some lead. So we are at equilibrium. So it'll be plus X, but plus 2X for the fluoride. So at equilibrium, the lead would be X and the fluoride would be 0.1 plus 2X. So we plug those into the expression. We haven't changed the temperature, so this is still the solubility product. So Ksp equals X times 0.1 plus 2X squared. Remember, we can do our shortcut. We can 5% rule this. 2X is going to be smaller than 5% of 0.1. So we can just ignore that part of the expression, 5% rule. Or, you could use it, you're going to get relatively the same number, whether you make the simplification or not. You can graph to solve for X if you'd like, okay? A lot of you know how to do that very quickly, so, you don't have to 5% rule, but, you can. And I think you get Desmos when you're taking the actual AP exam, so, if you could solve for X without doing the 5% rule, then more power to you, go for it, okay? But remember, it's about time saving, so if this is a time-saving thing, then go for it, okay? So 5% rule that. So we solve for X. So this is the new molar solubility, 1.8 times 10 to the negative 4. And let's compare that to the solubility in pure water. So in pure water, this was the solubility, 7.7 times 10 to the negative third. And notice that when we had a little bit of extra fluoride in our solution already, common ion, this is our new molar solubility, okay? Now again, this isn't the answer to party. This is the molarity of the solution, and now we got to do our dimensional analysis. Our goal was to figure out what volume of solution can hold 8 grams, basically, of lead fluoride. So we would take our 8 grams divided by the molar mass, divided by our new molar solubility to get liters, and then times 1,000. I think keeping it at liters is probably the best because we're going to need 180 liters to get 8 grams of the salt in that solution versus what was it from part C? Part C, we only needed 4.2 liters, but now we need 180 liters. So you can see how, just, the presence of that common ion makes the salt a lot less soluble. Okay, so 180,000 milliliters. Okay. Okay. So now let's go to part 2, and this is where we're going to be talking about, will we get a precipitate? Okay. So in part 2 of the question, we're mixing calcium chloride and silver nitrate. Okay, so, if we go back to unit 2 and our solubility rules, we should be, kind of triggered into going, oh, silver and chloride, that's going to precipitate because that's an insoluble salt. Like calcium nitrate, soluble. Calcium chloride, probably, soluble based on solubility rules. Calcium's not a exception for halide ions. But silver and lead will precipitate any halogen ion, right? So fluoride, chloride, bromide, iodide, just like you want to remember barium and sulfate, right? So a student plans to mix a calcium chloride solution with a silver nitrate solution to see precipitation. They want to see the precipitation reaction happen. And so part A is just, well, what would precipitate? And they want us the net ionic equation. So we'd have to be able to say, okay, it's just going to be silver plus chloride yields silver chloride, right? It's just a double replacement reaction. You got calcium chloride and silver nitrate. You would end up with silver chloride and calcium nitrate, but calcium nitrate would stay dissolved. So the calcium and the nitrate are spectator ions, and what you're left with is the silver ion plus the chloride ion yields silver chloride. Notice it's the reverse of a Qsp reaction, right? So a precipitation reaction is kind of the reverse of a Qsp dissolving reaction, right? So that's something to maybe make a note of, okay? So, if I mix that with that, I would expect silver chloride to precipitate, but maybe it won't, okay? So the question is, will it precipitate, okay? And what's going to make it precipitate? It's going to precipitate if these concentrations are oversaturated, and then some of it will stick together and form a solid, right? So they give us the Qsp, but understand the Qsp is the equilibrium constant for the reverse reaction that we wrote up here, okay? Whoops, okay, so we know the Ksp, and now we're given what volumes of solutions we mix. So we have the molarities up here, okay? And so we want to know when we mix 50 milliliters of this solution and 50 milliliters of this solution, will silver chloride precipitate? We expect it to because it's an insoluble salt, but the question is, are the concentrations high enough to be saturated or oversaturated to cause the precipitation? If we're undersaturated, then the silver and the chloride aren't going to precipitate out of solution, basically, all right? So this is, if you're trying to figure out if a precipitate will happen, this is a Qsp and Ksp question, right? Remember, Q is where you're at right now, and K is where you need to get to. Okay, so understand, we always say, like, if Q is greater than K, the reaction shifts left, because, come on back. All right. If Q is greater than K, you have too many products. But remember, we're talking about this reaction. So if Q is greater than K, that means you have too many aqueous ions, you're oversaturated, the reaction shifts this way, and you get the precipitate. But if Q comes out to be less than K, that means you're not oversaturated, you're not even saturated yet with the silver and the chloride, so you're not going to shift the reaction this way. And in fact, you could still add more solid silver chloride to the solution, and it's going to dissolve because you're not at the point of saturation yet, okay? So whenever you're trying to figure out if Q, or if an insoluble salt will precipitate, the question is Qsp greater than Ksp? If Qsp is greater than Ksp, absolutely. If you'll get a precipitate. If Qsp is less than Ksp, you won't see a precipitate. But we also have to be careful. Remember, we mixed 50 milliliters of this solution with 50 milliliters of this solution, so our initial concentrations aren't the initial molarities that were given at the start of the question. Our initial concentrations are going to be cut in half because when we mix them, we're doubling the volume. Okay, so you really have to do M1V1 equals M2V2. Now, we made the question a little easier here because we had equal volumes. So if you double the volume, you cut the initial molarities in half, right? So you could probably do it in your head. But if, it was 25 milliliters of this and, 8.6 milliliters of that, then you would want to do M1V1 equals M2V2 for each of your ions. And then you'd have to do M1V1 equals M2V2 for the silver ion and the chloride ion, and it's the M2s that you would be plugging into your Qsp expression, all right? And remember, a Q expression is equal to the same expression that the K is equal to, it's just you're plugging in initial molarities instead of equilibrium molarities, okay? So, and then the other trick is, so let's go back up here. Let's look at M1 for both of these. So M1 for silver is going to be 0.005, okay? But M1 for chloride isn't 0.0025, it's actually 0.0025 times 2, because this is the molarity of the whole thing, but you get 2 chlorides for every this. So another thing to watch out for is if you're given the molarity of the ionic compound that you're mixing together, that's not necessarily the M1 for that particular ion. We don't care, this is the molarity of calcium, but we don't really care about that right now. We care about what's the M1 for chloride. So M2 for chloride is going to end up being this number, okay? But that's because we got to double it, but then we doubled the volume, and then we divide by 2, so it comes back out to be the same, okay? So if you do M1V1 equals M2V2 for both the silver and the chloride, they come out to be the same number, right? The silver concentration was 0.005, and then it cut in half, and the chloride was also 0.005, not 0.0025, that was the calcium, but the chloride was 0.005, and then we cut that in half, and we got, our M2. So that's what you would plug into the Qsp expression. We don't have to square anything or cube anything because it's one silver ion and one chloride ion, so Qsp equals the silver concentration times the chloride concentration squared, okay? So we plug those in, and we get QSP, let's remind ourselves what the KSP was, 2.9 times 10 to the negative 6. And so this number, QSP, is greater than KSP. What does that mean? It means we're oversaturated with our ions, so the reaction would shift to the left, and which is the side of the precipitate for a KSP reaction, and so we would end up seeing a precipitate. So in this question, yes, the student would see a precipitate, and it's because the QSP that we calculated is greater than the KSP that we were given, right? So again, right, you were given the solubility product KSP, all right, and we just found out that we were oversaturated. So at the point of mixing, our concentrations of silver and chloride are oversaturated. Q is greater than K, so the reaction shifts to the left, boom, and we get a precipitate, okay? All right. And then, yeah, so part C, this was a tricky one, right? So notice they give us the solubility product of silver chloride at 75 degrees Celsius, okay? And notice that it's actually lower than the solubility product at 25 degrees Celsius. We went from 10 to the negative 6 to 10 to the negative 7. So K is decreasing as temperature increases. So that's telling us that the dissolving of silver chloride in water, the KSP reaction, is exothermic. But that's not what they asked. They asked the precipitation. They asked for this one. So we know that this process, solid silver dissolving to aqueous ions, is exothermic based on the KSP decreasing as temperature increasing. But they're talking about the reverse reaction, okay? And so if the forward process is exothermic, the reverse process is endothermic. So the dissolving of silver chloride is exothermic based on this information, but that would mean the precipitation of silver chloride is endothermic. So kind of a trick question there. A lot of you know that, okay, if K decreases as temperature increases, that's an exothermic process, but they weren't directly describing that process in that question, right? So we know that this process, based on what KSP did as temperature increased, we know that this process is exo, but that would mean the reverse process, the precipitation of silver chloride, is endothermic, okay? So just, be careful there, okay? And then the last problem, this is just calculating the molar concentration of chloride ions in a saturated solution at 75 degrees Celsius. So we got to know to use the new KSP value that they gave us. The KSP value is 75 degrees Celsius. And it's not a common ion question. It's just, hey, so use your KSP shortcut, solve for X. X is the molarity of the compound, but because chloride has a, subscript of 1 in silver chloride, X would also be the concentration of chloride ions. It's also the concentration of silver ions, okay? So the answer would be 5.5 times 10 to the negative 10 moles per liter, or capital N, for part 2, okay? All right, so that kind of takes us through the KSP review and QSP. If you really, if you followed that, you should be in great shape. Those are kind of the most challenging types of questions you'll see on the AP exam. So, especially like something like this one, and this one, like so. So you should be in good shape. All right. Have a great day.